I want you to picture a scenario.
Mm-hmm.
It's almost like the start of a psychological horror movie. You decide you want to learn something really complex, say the plot of the movie Tenet, or maybe advanced calculus. But first, we wipe your memory.
A total format.
Everything. You don't know what a movie is. You don't know your own name. You don't even know that gravity is a thing. You are a complete, total blank slate. And then I hand you a calculus textbook and just say, good luck.
That is, I mean, that's basically the tabula rasa problem. And for a
Yeah.
very long time, that's kind of how we've treated artificial intelligence.
Right? It's the standard inductive learning model.
Yeah.
We just throw a neural network at a problem and have to figure out everything from scratch, just from the pixels or the data points it sees in that moment.
Yeah.
It's so inefficient. And frankly, it's not how intelligence actually works.
Exactly. Because real intelligence, it relies on context. When you came into the studio today, you didn't have to relearn how to open the door. You used prior knowledge.
And that is the pivot point for this whole deep dive. We're looking at a text on the logical formulations of learning. We're moving away from that statistical guessing game and into a world where an AI uses what it already knows, its background knowledge, to learn faster and smarter.
We're going to get into how logic lets a machine use a current best hypothesis, how it can use explanations to build shortcuts, and this is the part that I think is really fascinating, how it can essentially act like a scientist, inventing new concepts to explain what it's seeing.
This isn't just pattern matching anymore. This is about discovery. But to get there, we first have to look at the flaw in that blank slate way of doing things. The source material uses the restaurant learning problem to set the scene.
A classic example. So you've got an agent, an AI, trying to decide if it should wait for a table at a restaurant. It looks at all these attributes. Is it a Friday? Is there a bar? Is it raining outside?
And normally, the AI builds a decision tree. If hungry and Friday, then wait. But the problem with that is that it needs a huge amount of data to be sure. It has to see every possible combination.
Because it assumes nothing. But if we switch over to a logical formulation, the AI isn't just counting examples. It's searching for a hypothesis. It's looking for a rule that fits.
And this goes way back to John Stuart Mill, right? This idea of a current best hypothesis.
1843. It's incredible how old these ideas are. The method is, well, it's pretty straightforward. The AI keeps a single hypothesis that explains everything it's seen so far. And it just treats that rule as the law of the universe until it hits a contradiction.
So let's say the AI's current hypothesis is something like, I will wait for a table if there are patrons inside. It treats that as a solid rule.
And you can sort of visualize that rule as a box. Everything inside that box is a positive example, a time you would wait. Everything outside is negative.
Okay, so then the AI goes to a new restaurant. There are patrons inside, but the wait is 3 hours, so it decides to leave.
And that breaks the rule. The hypothesis said wait, but the AI's action was leave. That's a false positive. The AI's box was, is too big. It captured something it shouldn't have.
So it has to shrink the box, has to specialize. It updates the rule to be, I will wait if there are patrons and the wait is short.
And of course, it works the other way too. If the AI skips a place because it looks empty, but later finds out the food's amazing and it should have waited, that's a false negative. The box was too small, so it has to generalize. It has to stretch the boundaries to include that new example.
It feels a lot like refining a Google search. You start broad, you get a bunch of junk, so you add quotes or minus signs to narrow it down, but just relying on one single best guess feels a bit risky. You're putting all your eggs in one basket when there might be other theories that also fit the data.
And that's the big limitation. You can get led down a really bad path, just constantly patching up a flawed theory. That's why the next step was the concept of version spaces. This was a huge leap. Instead of one best guess, the AI keeps every single hypothesis that hasn't been disproven yet.
That sounds like a memory nightmare. How can it store millions of potential theories?
Well, you'd think so, but here's the clever part. You don't actually store the whole list. You just store the boundaries. It's called the candidate elimination algorithm.
Okay, let's break that down. So you have boundaries. The most specific possibility on one side and the most general on the other.
Exactly. Think of it like a floor and a ceiling. The specific boundary, that's the floor, is the tightest, most conservative rule you can make that explains the positive examples. Something like, I only wait at this one specific pizza place on a Tuesday.
And the general boundary, the ceiling, is the broadest possible rule that doesn't accidentally include any of the negative examples you know about. Like, I'll wait pretty much anywhere that isn't actively on fire.
The truth is floating somewhere in the space between that floor and that ceiling. That space is the version space.
I see. So every time you get a new piece of data, either the floor moves up or the ceiling moves down.
Yeah.
The space between them just gets smaller and smaller.
And that's the key. The AI isn't guessing anymore. It knows with mathematical certainty that the correct rule is trapped in that shrinking gap. And eventually, the floor and the ceiling meet.
And boom, the version space collapses to one single point. You found the answer.
Ideally, yes. If your data is perfectly clean, you've essentially eliminated every impossible theory until only the truth is left.
It's pure Sherlock Holmes.
Yeah.
When you have eliminated the impossible, whatever remains, however improbable, must be the truth.
It is exactly that. But, and this is a big but, the real world is messy. If there's noise in your data, like you decided not to wait one day just because you had a headache, the version space collapses into nothing. The floor rises above the ceiling, the logic just breaks.
So pure logic can be a bit fragile. But let's look at where having that background knowledge really gives an AI an edge. Humans, we don't need 1,000 data points to learn a rule. Sometimes all we need is one.
That aha moment.
Yeah. The text uses this great story to illustrate it, the caveman Zog story.
Just a classic from the literature, yeah.
So you've got a bunch of cavemen trying to cook lizards over a fire. But they're doing it the hard way, holding the lizards in their bare hands.
Which, as you can imagine, results in a lot of burned fingers and dropped lunches.
Total chaos. Then Zog shows up. He grabs a sharp stick, skewers the lizard, and holds the stick over the fire. No burned fingers, perfectly roasted lizard.
Now, in a normal statistical learning model, the other cavemen would have to see Zog do this like 500 times to build a strong correlation between stick and success.
But they don't. They get it instantly. They all run off to find their own sticks. So why?
Because they have background knowledge. They already know fire is hot and causes pain. They know sticks are rigid. They know sharp points can go through meat.
So when they see what Zog does, they aren't just seeing raw data. They're constructing a proof in their heads. The stick is long, so the hand is far from the fire. The stick holds the meat. Therefore, the hand is safe.
And this is what we call explanation-based learning, or EBL. The agent uses its prior knowledge to explain the single example it just saw, and once it has that explanation, it generalizes it into a new rule.
It creates a rule like, long, sharp objects allow for painless cooking.
And here's the really cool part. The AI creates a shortcut. It essentially memoizes that rule.
This is that cheat code idea the text talks about.
Yeah.
EBL doesn't actually teach the AI a new fundamental fact about the universe. The cavemen already knew the physics of sticks and fire, but it teaches them a new use for that knowledge.
Right. I mean, think about calculus. The source used the example of differentiating x squared. If you have to prove that derivative from first principles using the basic definition of limits, it's a total nightmare. The text says it takes something like 136 logical steps.
That is 136 chances to mess something up.
But once an EBL system solves that problem one time, it looks back at the path it took. It realizes, oh, the specific number 2 didn't matter as much as the structure of the problem. So it generalizes the rule. The derivative of any u squared is just 2u.
And now it has a macro. The next time it sees that pattern, it doesn't do 136 steps. It does 1.
It turns complex reasoning into a simple reflex. That's a massive speed up. Alfred North Whitehead said that civilization advances by extending the number of important operations which we can do without thinking about them. EBL lets an AI do exactly that.
Okay, so we have logical search and we have these explanation-based shortcuts. But there's another huge problem with learning from a blank slate. Just knowing what to ignore.
The curse of dimensionality. I mean, the world has a basically infinite number of variables.
The Brazilian travel story in the text explains this so well. A traveler lands in Brazil. The first local she meets is named Fernando, and Fernando speaks Portuguese.
And she immediately makes a generalization. Brazilians speak Portuguese.
Which is a pretty solid guess.
Huh.
But here's the interesting part. She did not generalize that all Brazilians are named Fernando.
And just pause on that for a second. From a pure data perspective, the data set is identical. One subject. Nationality is Brazilian, language is Portuguese, name is Fernando. So why does our brain keep one link and just throw the other one away?
Because she isn't a blank slate. She has this background theory, a functional determination, as the text calls it. She knows that nationality generally determines language.
And she also knows that nationality has absolutely no causal connection to your first name. This is what relevance-based learning is all about.
It sounds obvious to us, but for an AI, that is a superpower. If you know which features are relevant, you can just ignore everything else.
Oh, the math on this is just staggering. The text explains that if you can identify the handful of relevant factors, like knowing that for electrical conductivity, temperature, and material matter, but the day of the week doesn't thus, you reduce the difficulty of the learning problem exponentially.
You go from searching the entire library to just searching one shelf.
Exactly that. You cut the search space down from, say, 2 to the power of n to 2 to the power of d, where d is just the small number of relevant things. It turns an impossible problem into a totally solvable one.
Okay, so we've filtered the noise, we've built shortcuts, but now we have to get to the heavy lifter. The technique that lets an AI really understand the complex, messy relationships of the real world. We need to talk about inductive logic programming, or ILP.
Right. This is where we finally get to leave the spreadsheets behind. Standard machine learning, what we call attribute-based learning, it loves spreadsheets, rows and columns. But the world, it isn't a spreadsheet.
The family tree example really drives this point home. If you want to teach an AI the concept of a grandparent, and all you have is a spreadsheet of attributes, name, age, eye color, you're going to fail.
We'll get these garbage rules like, if age is greater than 50 and name is Elizabeth, it completely misses the structure of the problem. Being a grandparent isn't a property of one person, it's a relationship between 3 people.
You need a language that can actually say A is the parent of B and B is the parent of C.
And that language is first-order logic. So ILP combines that powerful logic with inductive learning. It lets the AI discover rules based on relationships. It can look at a whole family tree and deduce that grandparent XY is true if there exists some Z, where parent XZ and parent Z.
It sounds like a detective putting together clues on a corkboard.
That's a great analogy. It literally uses a process called inverse resolution. Think about normal logic moving forward. If it rains, the grass will get wet. That's deduction.
So inverse resolution is walking outside, seeing the wet grass, and figuring out it must have rained.
You're running the proof backward. The AI sees the conclusion, the data, and it looks at its background knowledge, and it mathematically figures out the missing rule that must connect them.
But the text mentioned one ability of ILP that I found, frankly, a little spooky. It's called constructive induction.
This is really the frontier. Most AI learns to use the words and concepts you give it, but ILP can invent its own words.
New predicates.
Exactly. Let's go back to the family tree. Imagine the AI doesn't know the word parent. It only has data for mother and father. It starts working, and it notices that the rules for figuring out ancestors they're weirdly similar for both mothers and fathers.
It sees a pattern in the logic itself.
So it says, you know what? I can make this whole theory simpler if I invent a new concept that covers both mother and father. And it creates a new predicate, let's just call it piecewise DOS.
It just invented the concept of parenthood.
It created a new concept out of thin air to make its theory of the world more elegant. And this is exactly how human science progresses. Galileo didn't just measure rolling balls, he invented the concept of acceleration to explain the pattern he was seeing. Joule invented thermal energy. These concepts weren't just lying there in the data, they were constructed to explain it.
So ILP can do what Galileo did.
In a focused domain, yes. And we're not just talking about toy examples like family trees anymore. We really need to talk about the robot scientist.
This was the study by King and his colleagues in 2009. And this is where, for me, the implications of all this really hit home. This wasn't just a computer simulation.
No, this was a physical automated lab. The system was named Adam, and its job was to understand yeast genomics specifically, which genes were responsible for producing which enzymes.
And Adam didn't just passively analyze data that was fed to it.
That's the crucial distinction. Adam was an autonomous scientist. It started with some background knowledge about yeast metabolism. It looked for the gaps in that knowledge. It then formulated hypotheses, logical guesses about what a specific gene might be doing.
And then what?
And then it actually designed the experiment to test its own hypothesis. It chose the ingredients, controlled the robotic arms to mix the chemicals, ran the incubators, and then it measured the results itself.
It was doing the actual wet lab work.
It did the entire scientific loop. It collected the data, it used ILP to compare the results to its hypothesis, it updated its beliefs, and then it designed the next experiment to figure out what was still unknown. And it worked 247, no coffee breaks.
And it actually found things.
It discovered the functions of several genes that had been a mystery to human biologists for years, and it got the results published.
But here's the thing that I find most interesting about Adam compared to, say, a deep learning system like ChatGPT or AlphaFold. When a neural network gives you an answer, it's a black box. You get the result, but you have no idea why.
Right, it's just millions of numbers in a matrix. But Adam used logic programming. Its output wasn't a number, it was a logical sentence. It was gene A codes for enzyme B
It's
because
readable by a person.
it's a white box.
Huh.
A human scientist can actually read Adam's discovery, check the logical steps, and understand the mechanism. It produces knowledge, not just predictions.
That feels like such a fundamental shift. We're not just building tools that do the work for us, we're building collaborators that can explain their reasoning to us.
And that feedback loop is so important. If the AI invents a new concept, like we talked about with parenthood, it can actually define it for us. It can say, I've invented this concept X, and here is exactly how it relates to Y and Z.
So let's just wrap our heads around the journey we've been on. We started with the blank slate, the tabula rasa, and saw how incredibly limited that is.
Then we added logic. We used current best hypotheses and the certainty of version spaces to zero in on the truth.
We made things faster with explanation-based learning, turning reasoning into reflex, and we cut through the noise with relevance.
And finally, we unleashed inductive logic programming to understand relationships, to invent new concepts, and to literally run its own scientific experiments.
The trajectory here seems pretty clear. The more an AI knows, the faster it can learn the next thing. It's cumulative. It builds on itself, just like we do.
Which brings us to a fascinating and maybe a slightly unsettling final question.
The source material makes a pretty bold claim. It suggests that if you gave an ILP system the raw data of planetary motion, the trajectories of falling objects, it could, in theory, rediscover Newton's law of gravity.
It could effectively become Newton.
So here is the thought I want to leave you with. We saw how an AI could invent the concept of parenthood or acceleration to make its theories work. And those are concepts we can understand. But what happens when that AI is tackling a problem that we don't understand?
The alien science problem.
Exactly. What if an AI studying, say, dark matter or quantum physics invents a new predicate, a totally new concept that simplifies the theory perfectly, makes incredibly accurate predictions, and solves the whole puzzle? But the concept itself is something the human brain literally cannot comprehend.
If the equation works, but the variables are in a language we can't speak, is that still science? Or have we just handed the keys to the universe over to a machine that we can trust but can never truly understand?
That's a question we might have to answer a lot sooner than we think. Thanks for joining us on this deep dive into the logic of learning.
It's been a real pleasure.
We'll catch you in the next one.